I guess we'll start by talking about the derivatives of some log functions real quickly, and then we'll go back to vector functions and that kind of thing. All right. So, for example, if y equals ln of x, most of us know that the derivative of that is 1 over x. And if for some reason you had, y equals the ln of some, we'll say u, where u is a function of x, then really that's a chain rule situation, right? So y prime is 1 over u times u prime. The question comes up, well, what if you have the derivative in a different base? Like let's say, for example, I said, what about, just log x maybe, or y equals log base 7 of x, okay? If we just recall something from our past called change of base formula, it's not a big deal. Change of base formula says the following, that if you write log base a of b, then you can do the following. It's going to be the ln of b over the ln of a. That's what change of base formula is. Sometimes you write it log b over log a. You might have seen that in the past. Okay? As long as the bases of the log on the top and the log on the bottom match, you're fine. So that's how you deal with these problems. What you do is you rewrite log of x in change of base formula. You write it as the ln of x over the ln of the base, which in this case is 10. Okay? So I can think of this as a coefficient, 1 over the ln of 10, natural log of 10, times the ln of x. And then the derivative, it becomes more clear now, because when you go to take the derivative, all right, we've got a number multiplied by a function. The derivative of the function is 1 over x, and it just gets multiplied by that coefficient. So you get 1 over the ln of 10 times 1 over x, and that's not a dot product, it's just times, okay? So we're clear. You could do the same thing here. You can write this as the ln of x over the ln of 7. So then think of that as 1 over the ln of 7 times ln of x. And then your derivative, y prime, is the coefficient times the derivative of the function. Okay, and that's not probably how you might, if you looked up formulas in textbooks and things, you probably saw something like this. If f of x equals log base a of x, then f prime of x equals 1 over x ln a. It's probably what you saw in your mathematical past. And if you think about it, that's exactly what's happening here. We could write this, if we wanted to, as 1 over x times the ln of 7. It's always going to be the ln of the base of the log that you're taking the derivative of. If you had a function, instead of just x, you had some function of x, like maybe it was f of u equals log base a of u. So now u is some function of x. It has a derivative that's not equal to 1. So
f of x, right?
Okay.
F of u, then u is just a variable, right?
So yeah. So we really should be careful. Call this x maybe. All right, where u is a function of x. Then what happens? If f prime equals, well, it's going to be 1 over u times the ln of the base times the derivative of that inner function. And that's because of chain rule, right? So that's where these things come from. Well, that's just this. And so, for example, just in case we're not clear, on the log base a of b equals some number, all right? If you remember what the log question's asking, you'll be fine. When you write log base a of b, what you're really saying is this equals the power we put on a to get b. That's what log base a of b means. So I'm calling that power n here. I'm saying n is the power we put on a to get b. So a to the n equals b. That's how you take something in log form and write it in exponential form. Let's switch gears a little bit. So back to vector functions. Let's pretend they say R1 and R2 of t. Here are two vector functions that describe motions of two different particles or things flying through space. I'm telling you that they collide at a point. Just keep in mind, right? A vector function sort of describes a path through space. So maybe R1's path looks like this. It's a path with a direction. And maybe R2, its path looks like that. Okay? Keep in mind there's a difference between paths crossing and two objects colliding. These paths clearly cross. All right? It is true that for some value of t, there's some value of t here, and then maybe some other value, some different value of t along R2 where the paths cross. The question I'm interested in is, do they arrive at the same point at the same time? Because if they do, then they collide, right? So your job here was to try and figure out a value of t where that might happen, all right? So what that means is that all the coordinates, right, would have to be equal for the same value of t. So I would need cosine of t to equal 1 plus t. I would need sine of t plus 1 to equal t squared plus 1. And I would need 2t to equal 2t cubed. All right? So we know that one value t is going to have to work. So I would just start with the easiest equation to solve. That's this one. If you want those to be equal, right, what possibilities do you have? 0 would definitely do it. 1 does it, right? And I think -1 would do it also. Yeah, plugging any of those in would yield the same z values. All right, so now what we're going to do is try all these all out in the other two components and get them to match up. So let's start with 0. Say we start with 0. So if we plug 0 in here, cosine of 0 is 1. 1 plus 0 is 1. So far, 0 as a candidate works in the first place. It works in the third. If I put 0 here, sine of 0 is 0 plus 1 is 1. 0 squared plus 1 is 1. So, that works. So here's the point where they collide. Okay? Let's try 1. Cosine of 1 equals 2. That is not true. So this is out. Cosine of -1 equals 0. That's also out. So that one, the other two don't work. Right? Because as soon as I checked them, the x components didn't match up. Right? So now I know that when t equals 0, these two objects will collide.
Wait, you just chose 0, 1.
So you can start to think about, do these paths cross in any of the places? Which means that this value of t and this value of t could be different. Right? So let's think about that for a minute. Well, cosine of t, we thought of that as a graph by itself, looks like this, right? And then you have 1 plus t, right? Crosses at 0, and the question is, does it cross any place else? It doesn't. So that's out. Okay? But the idea of finding out what two paths cross is tougher sometimes because you'd have to consider plugging in different values t's for the left parameterization than for the right parameterization.
The t's on each side.
Correct. But like let's say for example, you'd have to make sure that you plugged in the same value of t here to get 1 point on R1, and then a different value of t here to get 1 point on R2, and you're seeing, hey, those 2 points the same at different times. It may or may not happen. That's always tougher. Luckily, we just had a collision question. All right. So now, let's answer some other questions. It says, find the length of the tangent vectors at the point of collision. All right. So tangent vectors, you get them by taking the derivative of the vector function. So R1 prime of t. You take the derivative of all its components. So the derivative of cosine is negative sine of t. The derivative of sine of t plus 1 is cosine of t. And the derivative of 2t is 2. And that's not really enough because they want the length of these things at the point of collision. So you have options. You could plug in 0 first, if you like. So let's do R1 prime of 0. And we would have negative sine of 0. Well, sine of 0 is 0, and negative 0 is 0. Cosine 0 is 1, and that's 2. Okay. The norm of that now is what we really want, because they asked for the length, would be square root 5. Okay, good. Do the same thing for R2 prime of t. Take the derivative and see what you get. So the first thing is 1. Second thing is 2t. And the third thing looks like 8t squared. If I plug in 0, I just get the vector 1, 0, 0. And the norm of that is just 1. So that's what they're asking for in this question. Oh, I think I made a silly mistake here. Hold on. This should have been 6t squared. It won't affect anything, luckily, because we plug in 0, but we should be careful. We want to make people doubt themselves.
What?
Now, sort of an interesting interpretation here, actually, of these things. Remember that these tangent vectors sort of give me the following information. They tell me when t equals 0, the exact direction we're heading in, and this sort of the speed with which I'm heading in that direction, right? And that's what you do. When you take the norm of these tangent vectors, this is how fast this object was moving in the direction of this vector. And this is how fast that object was moving in the direction of that vector. Okay, so you could think of this like position functions, velocity functions. The absolute value of velocity is speed, just like it was in a 2D world, okay, that you lived in. All right, took the derivative again, you'd have an acceleration, that kind of thing. All right, find the area of the parallelogram spanned by the two tangent vectors at the point of intersection. Well, you have two vectors, right? Here's one and here's the other, and they span out a parallelogram, like that. Okay. Now, ideally, for this problem, we hope you realize that you want the norm of the cross product. And we showed in the past, the norm of the cross product is the norm of one vector times the norm of the other vector times the sine of the angle between them. Okay? That's exactly the area of a parallelogram. You think about it this way. If this is vector A and you know its norm, and this is vector B and you know its norm, and you know the angle between them, you can get the height just by doing sine of theta equals h over norm A. Right? So there you go. You have another advantage in this case as well, if you notice. Let's do the work here. We're going to get an answer, and then we're going to be surprised. And then we're going to say something. Hey, we noticed something. So the norm of the cross product, we got to go do the cross product first. So it's I, J, K. And then the vector 0, 1, 2, 1, 0, 0. And I'm going to do this the quick way. So here's the first minor right there. It's going to be 0 minus 0. Here's the next minor is going to be 0 minus 2. But then I negate that, so it becomes positive 2. And then the last minor is this one here. So that's going to be 0 minus 1, which is negative 1. Well, the norm of that is square root 5. So for a second you might be surprised. You might think, hey, wait a minute. The area of this parallelogram had the same numerical value as the length of one of the vectors that was spanning the parallelogram. Right? Well, what does that mean? Right? It means that this vector on the bottom had length rad 5, and this whole area in here turned out to be rad 5. So it means the height must have been 1. Well, if the height was 1, that's exactly the length of the other vector. So you would conclude, hey, these vectors must have been perpendicular. So really, this particular parallelogram was a rectangle. But that's right. If you look carefully, you'll notice that these vectors are perpendicular. If you look at this vector here, right, there's 0 in the x component and numbers in the other two components. And then you look at this vector here, it has a 1 in the x component but zeros in the others. If you did the dot product, you'd get 0 right away. So that sort of reaffirms, hey, these two vectors really were perpendicular. Okay. All right. Last question. Find the equation of plane that contains the two tangent vectors you found in part B. All right, so we had our two tangent vectors. One of them was 0, 1, 2. And the other one was 1, 0, 0. The equation of a plane, you know, is the normal vector to these things multiplied by x minus one of the points it has to go through. Okay, so let's start to write that out. A times x minus x0 plus b times y minus y0 plus c times z minus z0 has to equal 0. Okay, well, luckily, we just did the cross product in part C. So there it is. So now we can write this. 0 times x minus x0 plus 2 times y minus y0 plus negative 1 times z minus z0 equals 0. So all I need now is a point that the plane goes through. we know the plane has to go through the point of collision, which happens when t equals 0, right? Because we did that in part A. So that's the key. Once we know that, we can go back to part A. Just look at that. Look at the vector function. Here it is up here, actually. I can pick 0, plug 0 into either one. So say I plug 0 into this one here. If t equals 0, I get back 1, and then 0, and then 0 again. So there's a point. T squared plus 1, actually. Sorry. So we plug 0 into here. We get 1 there. We get 1 here also, because it's 0 squared plus 1. And then that last piece is just going to be 0. So there's the point it goes through, 1, 1, 0. So we can sub that in and be finished. So 1, 1, 0. This first term's not going to matter. It's just going to go away, right? So the second term is 2 times y minus 1. And then really here, it's minus z minus 0, or just minus z, really. So there's the equation of your plane. If you want, what could you write? Y minus z equals 2. There you go. Don't forget the 2 there. 2y minus z. There we go.